struggled. Actually, I don't know if we've. I think there was a quiz question on this. But just the 4 phases of growth curves being the lag phase, the exponential, the stationary, and the decline phases. So if you were looking at a chart of your bacteria in culture, say at 24 hours, 48 hours, 72 and 96, theoretically, and this is what those equations that they were getting at, theoretically, bacteria always grow exponentially. So that's your theoretical curve, and that's going to be your n0 times 2 to the n is basically describing this curve. But in reality, let's change to red, your curve is going to look a little like this. And there's 4 different phases. So the lag phase is going to be this phase right here, which is where you don't see that exponential growth like you would theoretically expect, because the bacteria cells have to get used to the media that they're living in, make sure that they want to reproduce in that environment. The next phase you're going to see is that exponential phase. So it should mirror what you would expect theoretically, and you will see exponential growth during that phase. Your 4th phase is going to be your stationary phase, where you see that growth slowing down and eventually stopping. So the stationary phase happens because after bacterial cells are growing exponentially in a culture tube, imagine they're in a little enclosed environment, they're going to start running out of nutrients. There's going to start being competition between the bacteria. There's going to be death of bacteria. There's going to be waste produced by their neighbors. All those things are going to build up in this environment and slow down the growth of those bacteria. And then finally, you're going to get to a point where you start seeing a decline or a death in your colony. So these are just theoretical numbers, but you'll start seeing that decline phase where you lose bacteria because they can no longer survive, given the nutrients or whatever that's in this system. So wanted to address that. And then I also wanted to address these equations a little bit. I think the really important thing to understand about these equations are that when bacteria grow, so if this is our little bacterial cell, every generation you'll get double the amount of growth. And the way to show this, so basically that's like one bacteria splits into 2, each of those bacteria split into 2, and so on and so forth. This would be 1 generation, this would be 2 generations. And the way to show this mathematically is what they were talking about a little bit, is whatever your starting amount of bacteria, which would be n at time 0, or n naught, times 2 raised to the n. So this 2 raised to the n is showing that you'll have exponential growth by 2s. So in this particular example, if our starting number of bacteria, let's use a different color here. If this was our 1 starting bacteria, our n naught would be 1. And we would multiply this by 2 raised to the number n of generations. So n equals number of generations. And sub 0 is the number of starting bacteria. So our generations, in this case, it looks like we drew 2 generations. So this would be 2 raised 1 generation, 2 generation, raised to the 2. And then to write that out, or to do that math, it would be 1 times 2 times 2, because there's 2 2's, and this would equal 4. 1, 2, 3, 4. So this is just showing that if you start with 1 bacteria, after 2 generations, you'll end up with 4 bacteria. So what happens if we did 3 generations? So each of these bacteria then, multiply. So if we did this, our starting bacteria again would still be 1. You could change that to whatever you wanted and just do that math. Times 2 raised to the, this is our 3rd generation. So now we have a 3 generations. So this would be 2 raised to the 3. And how to do this math would be 1 times 2 times 2 times 2, which would be 8. So 1, 2, 3, 4, 5, 6, 7, 8. And this math works for however many generations that you have. So I think it's just really important to understand that bacteria will double each time. And the way to show that mathematically is with this 2 raised to the n. And you can always multiply that by however many you start with to get your overall number of bacteria. And I think they off the top of my head, I think they show that as NT, which is your number. This is your number at your starting point. This is your number at whatever time at 3 generations. At time t, basically. So yeah. Any questions about any of this stuff? Let's see. Or any other topics? Okay, so we have K equals N over T, and we have NT equals NO times 2N, our 2 equations. So we just actually did one of those equations. This is the equation that we just talked about, was NT equals NO times 2 to the N, and it just basically is this. So that's equation 1. The other one is K equals N over T. So previously we said that N is number of generations. T equals, I think, generation time, or incubation time, and K equals growth rate. So basically, what this equation is describing is a rate, which is always going to be the slope of a line. So if we were looking at this on a graph, we would have our incubation time down here, for example, like 24 hours, 48 hours, etc. I can't write apparently. And here we would have, each of our generations of bacteria. And K would be the slope of the line. If this was our theoretical growth of our bacteria, K would be this growth rate. So you could have bacteria that grew slowly, or you could have bacteria that grow really quickly. So K is going to vary just how fast the colony is growing. So what they were talking about in the equations was combining these 2 equations. So if this is equation 2 and equation 1, let's write it on here, was KT equals, that's not right, NT equals, sorry, NT equals NO, so whatever we start with, times 2 to the N. What they were talking about is solving for K or T given NT or NO, your starting number, or your, what did we say NT was? I don't even think I wrote it there. Number at time T, basically. So basically your ending amount. You can solve for your growth rate or the incubation time. I think usually you want to be solving for that growth rate because you want to know how fast your colony is growing. So in order to do this, you can combine them with this variable n, because n is the same in both of these equations. So let's draw a little box here and solve for this. So to combine it, I would take equation 1, nt equals no times 2, and it's raised to the n. So instead of n, I'm just going to put in what this would equal. And we didn't talk about this yet, but in this equation, you can also write it two other ways. You can write it as t equals n over k by multiplying each side by t and then divided by k. Or you can also write it as n equals k times t, because you would just multiply by t to move it over here, and then you have t times k equals n. So these are just three different ways of showing the same equation. So we can put in k times t here. And then in order to solve this, we would divide, just use a different color here. We would divide both sides by NO to isolate your k and your t. So this would be NT over NO is equal to 2 times k to the t. And then in order to bring this exponential, because this is an exponential function, down to where you can work with k and t, you would take the log base 2, because this is a base of 2 for this log. The log base 2 of each side. So this would go to log base 2 of nt over no is equal to k times t, because you've gotten rid of this exponential function. And then in order to solve for k, you would just divide both sides by t. And I'm running out of room here, but our final equation would look something like nt over no over t equals k. Does that make sense? So this is just getting a little bit more theoretical, but it shows that if you knew how much bacteria you had in your sample, and you knew how much bacteria that you started with and how long you grew it for, you would basically be able to solve for the slope of this line. Sorry, I have to go shut off an alarm. I'm sorry, it was a little messy there.